Right. So the title of this talk is Bridge Model. Bridge model updating as a digital twin technology disconnects between academic research and industry practice. So I will first define some of the terms in this title. So first of all, digital twin. So it covers a lot of things here, but the general description is to have a realistic digital copy and representation of the physical world. So in this case, we're looking at the bridge structure. So because it is a realistic one, so rather than interact with the physical structure, we can now interact more with this digital copy. So for example, to run some simulations of different scenarios, to make predictions about the performance, and to provide feedback into the physical structure, etc. So basically, it's intended to be something you can put in a control room and do some remote management for bridges. So that's digital twin. So model updating is intended to be a digital twin technology. So basically, it's about how you integrate your collected measurement data with your digital model. So for example, an analytical model of the bridge structure. So I will talk a bit more about this later in the talk. So as we all know, bridges are critical transport infrastructure in our living environment. It can connect different regions together and have significant social, economic, and environmental impact. So this is where I was born 26 years ago in the southern part of China. So this bridge, it links two cities together and makes people's lives much more convenient. So it was designed and built around 80 years ago, and it is still functioning very well today. So it's a road and railway bridge, so with trains passing inside the truss and other vehicles at the top. That's one type of bridge we're looking at. So then my family moved north to Beijing, the capital of China. So this is another type of bridge where you can see more often in your life. So the standardized concrete bridges carrying road traffic, and often they are reinforced concrete, but sometimes can be pre-stressed concrete. So then around 8 years ago, I traveled to England to study for A-levels and university degrees here. So this is the River Thames in London, and the bridges in England or in the UK are quite different to the bridges in China in many ways. So for example, even though there are lots of ancient bridges in China, most of the concrete bridges in China are fairly new. So most of them were built after the 1980s, whereas here in the UK, a large number of concrete bridges were built 60 or 70 years ago. And we know concrete deteriorates and has a big problem called corrosion. So there is a potential problem here. So because these concrete bridges are 60 or 70 years old, at some point in the near future, these bridges are collectively going to approach their end of life state. And we would have to either demolish these bridges because of the corrosion problem or refurbish them to extend their service life. And we know that because of climate change, there is going to be a problem of carbon emissions if we choose to demolish all of them. We need to better maintain our existing bridges because of the continuing bridge deterioration and asset time bomb problem, and also there's a pressure from climate change. And better maintenance relies on more reliable examination of the current condition. So this is mostly based on visual inspection in current practice, and many studies have shown that bridge inspection has its own problems. And I will just mention one of these problems. For bridge inspection, for bridge structures in general, the devils are most often in the details and they are difficult to inspect. So for example, this is the I-35W Mississippi River Bridge in Minneapolis. And if you look at the right-hand side, if you look at this joint, in general, it's quite possible that you won't spot any critical problems. If you look in detail, there is a slight buckling of the plate, indicating that the plate is overstressed and probably too thin. So if the inspector or the engineer doesn't have enough engineering knowledge about the bridge behavior and performance, so this problem will probably go unnoticed. And that can cause catastrophic consequences. So this is the same bridge. So the slight irony about this bridge collapse is that the bridge was inspected quite frequently and in detail because they already knew that it's a structurally deficient bridge, so they paid a lot of attention to it, but the bridge still collapsed. So to address these problems, a lot of the researchers, especially since the 1990s, have been saying that we need to measure the real performance of the bridge rather than just rely on qualitative visual inspection results, which are highly variable and subjective. So we put sensors onto a bridge to measure all kinds of things such as strain, displacement, acceleration, weather conditions, loading, etc., and call it structural health monitoring. So the general concept is, using the analogy of human health monitoring, is that the comprehensive sensing system measure the performance of our human body and provide feedback into a central brain power to diagnose potential health problems. So we're trying to borrow the analogy here to our bridge structures. So 20 or 30 years have passed since that concept first was proposed. If we now look at the industry still relies heavily on bridge visual inspection, and there is little sign of there's little sign of the industry practice shifting more to structural health monitoring for bridges. So basically, research and practice are not talking to each other in this field, and we need to ask why. So for example, we need to ask questions like, what are the industrial values of having structural health monitoring for bridges, and what are the low-hanging fruits here to drive industry adoption? And also in terms of digital model updating as a digital twin technology. So first of all, this is basically combining physics-based analytical model and field measurement data to create a realistic digital representation of the physical structure. And we need to ask, how is that going to be helpful for bridge operation, maintenance, and where should we focus on? So that brings to the subject of this study, which includes 19 semi-structured and in-depth interviews with expert bridge professionals in the UK to address the question of, can and how can bridge monitoring, modeling, and model updating as a digital twin technology be implemented in practice for better maintenance of new and existing bridges? So the outline of this talk, so I will first give some more background knowledge and the state-of-the-art review on bridge monitoring, modeling, and model updating research. And then I will present the findings of the industry interviews. So that includes what is the current practice on damage detection, structural assessment, bridge monitoring, and bridge modeling. What are the industry's views on adopting bridge monitoring, modeling, and model updating in practice? What are the key structural issues that could keep them awake at night, and what are the key required capabilities by the bridge practitioners? And finally, I will summarize the findings and present some recommendations. And the recommendations are, which is basically addressing any of the issues raised in the interviews. So let's first look at research. So bridge monitoring in research. So it often started with sensor deployment studies and model validation. And by sensor deployment studies, I mean that validating the measurement technologies we developed or we have. For example, to what degree of accuracy and precision can we measure various types of bridge response, so something like that. And then we go to model validation. So that is basically we compare our measurement with model predictions to see how accurate our model is in predicting the performance. But these two alone are not structural health monitoring. So in terms of health monitoring, the research is mostly driven by anomaly detection and damage detection. So anomaly detection is basically, from the data itself, we establish a normal behavior, so we call it performance baseline, and any subsequent deviations from that performance baseline, we can flag that as an anomaly. So that's anomaly detection. It's more of a data-driven approach. And damage detection is more building on that to look at what's behind that anomaly, and is there a damage? Is there a damage there? So in research, it often started with stiffness reduction. So we look at the measurement data to see if there is any reduction in stiffness, and try to relate that stiffness reduction to certain damage scenarios. But that is a very general approach. So Then researchers have looked at more specific damage scenarios and starting from cracking. So basically, if there's a cracking in the beam, we would expect that if we measure the strain in the beam, there might be localized increase in strain due to cracking, and also we would expect that there is a shift in the centroidal level of that beam. But cracking is not the main concern of many bridge owners. So other people have looked at more concerning damage scenarios like bearing seizure, fatigue life assessment, and more recently scour. And there are also other key areas of interest in monitoring research. So I will just mention a few of them here. So the general studies on the dynamics and vibration of the bridge structures, looking at what's the dynamic properties of that bridge. And we know that the environmental trends have a big impact on the bridge response. And how can we remove that environmental trends when we try to detect if there's any anomalous behavior? And the other thing we are interested in was the real loading on that bridge. So so that's kind of like the real supply side. And if you have the real supply, then you also the real demand. So if you have the real demand, then you are also interested in the real supply, which in this case, how much load can be carried by the bridge. So which is load rating and capacity assessment. And also some researchers have been looking at the fundamental engineering physics of the bridge structures, which I call it structural behavior mechanism. So that's a very general overview of bridge monitoring in research. So there is a commonly adopted four-tiered approach in structural health monitoring research, especially when it comes to damage detection. So starting from damage existence and type. So is there a damage and what is the damage type? And then look at the damage location. So can we detect where is the damage? And then it's damage extent and severity and the reasons behind it. So basically how severe is the damage and why is the damage happening? And finally, looking at prognosis. So basically, can we do some early warning and predictions of remaining service life? So that's on the research side. So as for bridge modeling in SHM research, so it's predominantly finite element modeling and mostly for model validation and updating. So basically looking at how valid is your model in predicting the performance of the bridge. And some of the more recent questions in this area include, is a simple model possible? So we know that designers prefer a simple model, at least for the global structural behavior, because they don't worry too much about the real behavior of the bridge because of the lower bounds theorem. But what about operation and maintenance? Can we use a simpler model, or do we have to use a very complicated model to capture the real behavior? And next one is understanding of structural behavior. So finite element model, sometimes if it's not used correctly, may not be the best model in terms of understanding and explaining the structural behavior, and how do we address that? And finally, is there any new modeling and analysis technique that's both accurate and interpretable? So finally, bridge model updating as a digital twin technology. So we have looked at bridge monitoring and looked at bridge modeling, and we're trying to combine them together. So how can we create a more realistic digital analysis model to run simulations? So the research methodology is essentially an inverse problem. We have some measurement data, so we get the measured performance from the monitoring data. And on the other hand, we also have predicted performance from physics-based structural modeling. And quite often the case, there's a gap here. And if we can trust the data, so then we trust that the measurement is correct, then that means that there's something wrong with our model. So a general approach is that we minimize the discrepancies between the model and data by updating uncertain model parameters in that model, and in the hope that the updated model will be a realistic representation of the physical structure. So there are, in terms of actually implementing it, there are three categories of approach. So the first one is to match identified model properties, so often measured under ambient vibration. So this is based vibration-based approach. And the next one is to match strain or displacement response on the controlled load test. So basically, we probably need to close the bridge and we apply the loading of a vehicle, and the loading is already measured. So we can also measure the performance under that particular loading. So by linking the loading to that response, we can infer what's the structural properties of the bridge. And the next one is mostly for masonry arch bridges. So because we know that for masonry arch bridges, the safety of the bridge depends on its stability, and the stability depends on its geometry. So we need to so we can do some laser scanning to get the deformation geometry, and using that to update our model. And in terms of the updating technique, so how exactly are you going to do that in the process? So starting from the manual tuning, so basically it's a manual process. So you look at the data, you look at your model predictions, and you interpret what's behind that discrepancy. This is mostly based on engineering knowledge and judgment. And sometimes there's an iteration of trial and error going on here until you get a satisfactory result. And then people have looked at more automated approach. So the first one is residual minimization. So basically, you set your objective function to be the discrepancy between your model and data. And using some analysis, you can say that that discrepancy is due to certain number of parameters. And you frame that as an optimization approach. And you frame that as a deterministic multivariate optimization approach. Yeah, and next, then people say that we can't just have a deterministic approach. We need to have a probabilistic approach to assess the risks. So there are Bayesian model updating and error domain model falsification approach. So the Bayesian model updating is basically update your prior knowledge about the bridge structure using monitoring data through a Bayesian inference approach. And error domain model falsification. So the method is to falsify models from a population of candidate models by performing a threshold check on the model data discrepancy. And the threshold value is based on the model and data uncertainties. And recently there are some machine learning based techniques, and I'm still learning about it. And so far these are more of a case by case basis. So now let's look at bridge model updating as a digital twin technology. So as I mentioned before, so here is a general description of digital twin. So it's not a proper definition, but it's a general description that we can rely on to guide us to do some research. So it says a digital twin serves as a virtual representation of the physical infrastructure, which can be updated in near real time as new data is collected, provide feedback into the physical structure, and we can use that to perform what-if scenarios for assessing asset risks and predicting asset performance. So if we think about actually implementing it in practice, there are some practical implications of that. So first of all, having a digital twin means that we need to have a simulation model that lives with the structure. So basically, that model is going to be kept on a permanent basis and needs to be frequently used. Otherwise, what's the point of having that model? The next thing is there needs to be continuous measurement data coming from a robust monitoring system so that we can have updated information, basically real-time information about what's going on with the bridge structure. And because there are continuous measurement data coming in, we can't do this can't do all of the process manually, so there needs to be some sufficient degree of automation. And finally, the vision is that by having that digital twin, we have real-time information about our bridge structure. Now we can do some remote management and hopefully proactive maintenance of bridges. So that's some background knowledge on the research side. So now let's look at the industry side. So I did a series of industry interviews over the past 2 years. So they are semi-structured interviews with 19 expert bridge professionals. So in this case, owners, operators, and consultants in the UK, basically looking at what are the industry perspectives on having monitoring, modeling, and model updating in their practice under the broad context of the day-to-day practice and decision-making in bridge operation maintenance. And it covers a broad range of bridge operation maintenance scenarios. So, for example, road bridges and rail bridges. Some people are operating at national level and some at regional and local level. Some bridge owners have a large portfolio of bridge assets to manage, whereas others, they might only have one or a few landmark structures. And it should be noted that although it's limited to the UK context, then portable insights can be obtained from this. So let's look at some scenarios first. So this is the Clifton Suspension Bridge in Bristol. So some bridge owners only need to look after one or two bridges. And the bridge owner for the Clifton Suspension Bridge only has one task, and that is to make sure that the service life of this bridge is infinity. And she only needs to look after this one bridge. And her office is basically a 30-second walk from this bridge. So she can see what's going on with the bridge almost all the time. And then this is a quite different scenario. So this is the M25 road network. So the consultant is employed to look after the whole network with probably 30 or 40 bridges and also loads of other assets. And his office is, of course, very far from here. So he needs to prioritize a lot of things and come up with a work plan to do the maintenance and refurbishment for all of these assets. And you can already see that these two scenarios are quite different and therefore have different implications on potential deployment of bridge monitoring and digital twin technologies. So back to this interview. So the contents of this interview include 6 areas. The first one is key structural issues that keep bridge practitioners awake at night. Current practice for for damage detection and structural assessment. Current practice for bridge monitoring and modeling, if there is any. The barriers and incentives to using bridge monitoring and modeling. The industry perspectives on bridge model updating as a digital twin technology. And finally, key capabilities required by the bridge practitioners. So I'll be mainly focusing on these two, but I'll also briefly mention the findings from the other ones. So, so key structural issues that keep bridge practitioners awake at night. So the common reasons for keeping them awake at night, there are 4 common reasons. The first one is that the bridge component or structural issue is safety critical. Basically, if there's something wrong with that bridge component, then there's going to be a big problem for the whole bridge. And next one is the bridge defect or bridge component is difficult to inspect. So for example, hidden defects. And next one is the bridge issues are difficult to manage and maintain. So a typical issue for bridge operation and maintenance is waterproofing, because waterproofing almost always failed, and that can lead to problems like material degradation. And finally is lack of engineering understanding of certain issues and limited forewarning for certain failure modes. So for example, for example, some failure modes is pretty sudden and unpredictable, so that can cause a problem. So the commonly raised structural issues in the UK context. So the first one, the top one, is material degradation, such as corrosion and fatigue. The next one is joints and bearings, and third one is bridge scour, and there are also a lot of other issues. So current practice for damage detection and structural assessment. So in damage detection, it's predominantly by bridge inspection. There are also some public reporting and other reporting mechanisms. So basically, if you're on the bridge and you notice something is wrong, then there's a way for you to report that problem to the bridge owner. And in terms of using testing and monitoring, they are mostly reactive and in a targeted manner. So to investigate a known damage picked up by bridge inspection rather than detecting any damage in a proactive manner. So for structural assessment, basically capacity assessment, it is not a priority for bridge owners and operators. The frequency is very low, so basically once every 18 years for a bridge. And there are 3 levels of assessment, starting from the simplest model with the most conservative assumptions, and if that doesn't work, then they go up and to a higher level of assessment by using more complicated model and less conservative assumptions, for example, from inspection results, testing data, and sometimes monitoring results. This is the standard I mentioned. So there are 3 levels of assessment for bridge operation and maintenance, and for majority of the structure, level 1 is enough. So they can do a simple structural analysis and using some conservative assumptions. So if you think about it, then in terms of finite element modeling, that's level 2 and level 3. So if modeling in general is once every 18 years, then finite element modeling is even less frequent in bridge operation and maintenance. So now let's look at the current practice for bridge monitoring and modeling. So as you would expect, that there's very little use of bridge monitoring in practice, and there are some used. So the most common types of bridge monitoring used in the current practice in the UK, the most common one, starting from the most common one to the least common ones. So the most common one is wind and flooding measurement. So basically, you measure the wind speed and the flood level, and you set some threshold levels. So basically, if that wind speed or flood level is above that level, some actions need to be taken. So for example, if the wind speed is too high or flood level is too high, then you probably need to close the bridge for safety reasons. So that's a very straightforward approach. So the next one is bearings and joint movement along with temperature measurement. So basically they want to check that if the bearings and joints are moving properly, and if it's not moving properly, then it's going to be a local stress buildup, and that can cause a change in local and global structural behavior and potentially overstressing some bridge components. So they need to make sure that the bearings and joints are moving properly. The next one is a dynamic response. So this is more from a serviceability point of view. So basically, you don't want the bridge to be too wobbly. So you measure the dynamic response to ensure that there's enough damping in that bridge. The next one is wire breaks. So you want to make sure that the bridge has enough wires to carry the load for the bridge. When in motion, you want to understand what's the real loading on the bridge, and crack width. So this is mostly for investigating certain damage, certain cracks which are critical. So looking at if the cracks are propagating or if it's is that crack, should they worry about that crack or not? So that's monitoring. So for bridge modeling, again, very little use. So once every 18 years. And when it comes to FE modeling, it's even less frequent. And the existing practice for modeling, so they are predominantly a one-off exercise in a targeted and reactive manner. So they are not keeping that model. So they build a model from scratch, and then once they have done the analysis, then they basically dump that model. And the modeling is driven by capacity assessment, and sometimes for analyzing critical components with known issues. Basically, if they're worried about certain components, let's say a joint, they want to make sure that joint is not overstressed. So they do a FE analysis to look at the stress distribution of that component to see if that joint or that component is safe or not. So now comes to the main questions. So what are the barriers and incentives to using bridge monitoring and modeling in practice? So we start from bridge monitoring. So there are 4 key barriers. The first one is cost. And by cost, they specifically mean first cost, which is basically cost at present. They are not very interested in the whole life cost. They are looking more at the cost at present, because there's also pressure from the budget constraints. So some quotes here: the budget has been limited and probably increasingly so for their bridge operation and maintenance activities. and more money on monitoring means less money on repair. So, so they have a limited amount of budget. And if you say that you need to put more money on monitoring, that money comes from the money from repair. So it can be difficult to justify the reasons why you don't want to spend that money on direct repair, but you want to spend that money on monitoring because the money on repair is already limited. The next one is the value case for monitoring. So there are two types of monitoring we're looking at. The first one is reactive and targeted monitoring. The second one is proactive and less targeted monitoring. So the reactive ones are basically you pick up that damage from your visual inspection, and you are worried about that damage. You want to know what's the real performance, whether it's the whole bridge structure or whether it's that local area, and you put some sensors to understand what's the real performance, and you then examine whether that damage is critical or not. So, so you can already see what's the outputs and benefits of that monitoring. So it's easier to justify the value case. Whereas for proactive and less targeted monitoring, so basically you want to put some monitoring in to pick up any problem, but because it's less targeted, first of all, you probably need to put more sensors on the bridge because you are trying to pick up a lot of different problems. And the next one is the bridge probably won't fail, so you don't know when the benefits is going to come up. So if the bridge is not failing, then you're just putting sensors there to check if the bridge is working properly. So there's whole loads of issues with actually implementing proactive and less targeted monitoring. So, and here's a case study, which is if you're more interested in this area, I would suggest that you should look at this case study. And the next one is the post-processing of structural health monitoring data. So basically addressing the question of what are you going to do with the data, especially if there is a large volume of data coming in. So at the moment, there is probably no satisfactory answer to that. So we as researchers still need to work more on that. So currently, most of the structural health monitoring deployment is basically measurement for measurement's sake. And the last one is still, and it's also a very important one. So the reliability, robustness, and future-proofing of bridge structural health monitoring system. So basically, based on some people's experience, the bridge structural health monitoring system deteriorates much faster than the bridge itself. So if you put a monitoring system in and the bridge has not failed it's not going to fail for 30 or 40 years time, but you need to constantly replace that bridge monitoring system. That's not a very ideal scenario for the bridge owner. And there's also a problem with system updates and technology upgrade. So is the monitoring system you put in valid in 30 years time? So those are the barriers for bridge monitoring. So I mentioned this case study before. So this is an article called, the title is Smart Infrastructure, Are We Delivering on the Promise? So there's a case study on the new Watson on Times Bridge to illustrate the challenges of implementing proactive monitoring in a cost-effective manner. So if you're working on proactive monitoring and maintenance, or if you're interested in this area, I would highly recommend that you look at this case study to have some understanding of what are the practical implications of doing that. So here's the bridge in this case study. So now let's look at the incentives. So because they don't have many of the practitioners don't have very detailed knowledge of bridge monitoring, so it can be a challenge for them to come up with clear incentives. But here are some incentives mentioned during the interviews. The first one is, if we put some monitoring in, can it be used to help me reduce the cost? So can we achieve cost reduction by reducing risks and uncertainties? So for example, using reduced safety factors to allow us to do more targeted maintenance and refurbishment. And when it comes to refurbishment, so the problem with doing refurbishment is that if we don't have the knowledge of the real structural behavior and performance, then we need to make a lot of very conservative assumptions when we do the refurbishment, and sometimes it can be quite challenging. So having that knowledge of real structural behavior and performance will be very helpful, especially when it comes to doing refurbishment. And the final one is basically a general vision for bridge monitoring is, can it help us to do remote management and proactive maintenance of bridges? So now let's look at bridge modeling. So the key barriers, the first one is the modeling issues. So what model complexity? So because we know that for different use cases, we need to have different model complexity. If it is not a one-off exercise, if we are going to keep that model on a permanent basis and potentially to cover a large range of different use cases, then what model complexity should we choose? So that's a problem that needs to be addressed. The second one is end objectives and benefits. So currently in the current practice, the objective of modeling is driven by capacity assessment, and the bridge owners prefer using less and less modeling because they think it involves too much cost. So we need to have more benefits coming out of bridge modeling in order to justify the cost involved in that. And there are also practicality issues. The first one is the cost-benefit analysis. This needs to be done to justify the use of bridge modeling. And the second one is the liability of keeping an FE model. So the bridge owners tend to avoid having an FE model, keeping an FE model with their structure because they see it as a liability issue. So basically, if they keep an FE model, then they have a legal obligation to check that FE model, check that the model is correct. And because most bridge owners don't have an engineering team to do that, then they're trying to avoid that risks by basically saying, I don't want to keep an FE model with me. And the other issues is that FE software package and system update. So the service life of a bridge, let's say 60 years. So the model I created, let's say, is using some software version 10, and in 20 years time, it's like version 25. Is my model created now still valid, or do I have to constantly change my model? Incentives. It's even more difficult for the interviewees to come up with clear incentives of having bridge modeling because in the current practice, the frequency of having bridge modeling is extremely low. But there are still some suggestions. So for example, if there is an ongoing management situation where there might be an incentive to retain an FE model for engineers to refer back to. So basically there needs to be some scenarios where this is mostly for, let's say you have specific issues with that bridge and you know that you need to constantly look after that bridge, and then there's probably an incentive for you to keep an FE model because you need to keep an eye on that bridge on a very frequently. And the other incentive for having an FE model is to assess risks and evaluate criticalities and vulnerability of the bridge structure. So basically, by having an FE model or a structure model, can it help us to do more targeted maintenance and refurbishment? So I just need to look at those critical and vulnerable areas rather than look at the whole areas of the bridge. So the next one is industry perspectives on bridge model updating as a digital twin technology. So I'll first present some background here. So not surprisingly, nobody had heard of the inverse problem approach in the academic research. And some uses a forward problem approach. So basically, if they want to create a more realistic model, rather than measuring the response of the bridge and then make some inference about what's the bridge properties, they just directly measure the bridge properties. So for example, they use laser scanning to measure the geometry. They do some material testing to have some understanding of what's the material properties. And in terms of boundary condition, we can probably do some visual inspection to see if the bearings are working or not. And nobody uses modeling for damage detection, which is what's happening in research. And modeling is driven by capacity assessment in practice. And FE modeling is very rarely used for bridge operation and maintenance. So for them, it seems to involve a lot of effort and cost, but not too much value if it's not driven by capacity assessment. That's their opinion. It might be right or might be wrong. So on the academic methodology of inverse problem, so the academic approach relies on the key assumption that localized damage results in local reduction in stiffness, which is subject to questioning for some damage scenarios. So for example, for concrete corrosion, we are also looking at reinforcement corrosion, the corrosion of reinforcement and pre-stressing tendons. The experimental studies have already shown that the effect of concrete corrosion on the stiffness reduction is very small. So if you want to see if you want to actually measure the reduction in stiffness from concrete corrosion, you need to have a very severe concrete corrosion to make that happen. But if you have very severe concrete corrosion, you probably already pick that up by your visual inspection. So then you don't really need to put your sensors in. And it is also unclear exactly what structural damage can be detected. So far we know that based on the previous slides, we know that the bridge owners are worried about corrosion and fatigue. So these two are the main issues. And these two, so far, seems to me that it cannot be addressed by this methodology, at least now. And there are also some other general comments about this. So if it's not linking, because doing modeling involves a lot of work. So if it's not linking damage to capacity, the bridge owners are generally less interested, because if they make some investment on modeling, they want more coming out of it. And there needs to be sufficient verification, validation, and engineering interpretation for them to trust that model. So especially, here's the key question. So is the updated model valid under different loading scenarios of interest? So basically, if I update that model using some measurement data on one scenario, is that model still valid if I'm looking at another scenarios? And the final one is, does that help me better understand the real structural behavior and performance? So we have already mentioned that FE modeling in itself may not be the best option for this. And finally, we also need to look at what are the key capabilities required by bridge practitioners. So there are 4 overarching questions we need to look at. So first one, is the bridge safe? And the second one, how long will the bridge or bridge component be safe? And third one, how is the bridge behaving and responding? And when and how to intervene. I'm running out of time, so I'll just very quickly mention these. So here are some key capabilities required by the bridge practitioners. So damage detection, so they're interested in early warning and real-time detection, and also hidden defects. Damage criticality evaluation. So for example, there are thousands of cracks on the bridge. Which one should they intervene? Load capacity assessment, remaining service life predictions, especially for bearings and joints. And finally, what-if scenarios, because there is going to be a change of loading, and because of climate change, extreme events in the future. Yeah. So I'll come to the recommendation. So basically, the recommendations are we need to address all of the issues raised in the industry interviews. So I grouped them under 4 categories: accuracy and interpretability, use case and usefulness, efficiency and practicality. So basically, we need to make sure that whatever process we're developing, or whatever new tool or new technique we're developing, first of all, we need to demonstrate that there's enough accuracy of that. And also, they don't want a black box. So we need to make, so what they want is something that they can interpret. So is there a way that we can make that process interpretable so that the engineers can understand? And the next one is use case and usefulness. So they are not interested in very general damage detection. They're interested in specifically what damage scenarios are you looking at? On efficiency, so because it's going to involve a lot of data, so how do you automate that process, but still without losing the engineering insight? And finally, there are lots of practicality issues I already mentioned before. So this is the slide, the second last slide I want to show. So it seems that there are a lot of challenges we need to overcome. But the general approach is that the cost of technology will go down. So hopefully will go down. So as researchers, we need to work more on the benefit. So far, the rate of increase in benefit is incredibly slow. So we need to work more on that. And also, we need to make sure someone needs to look at the low-hanging fruits of bridge monitoring to drive the industry adoptions. We can't all work on very futuristic research. Someone needs to look at, if we are going to deploy a monitoring system, what can be done today to have real benefits now or in 5 years' time. And finally, this is a bonus slide from Peter Colley from Imperial College. So he's talking about structural health monitoring adoption. So it says SHM adoption will be a gradual process, and it may be fruitful to consider what makes potential applications likely candidates for early adoption. Favorable cases include structures where, one, there's no enormously over-designed reliability built in, like a bridge where the economic case is likely to be weak. This is definitely not ideal for bridge structures. The second one, structural failure will have severe economic consequences, but is not likely to lead to loss of life. Again, not the case for bridges. The third one, critical damage occurs on relatively short timescales, so replacing the frequent inspections that would be necessary if standard non-destructive evaluation is used is attractive. Again, the critical damage on bridges occur on relatively long time scale, so the benefits of replacing that is going to be challenging. The fourth one, current inspection methods are inadequate in some way. For example, access is difficult and so expensive and disruptive. To a large extent, this is true for bridge operation and maintenance. And finally, regulation standards govern at least some aspects of the process. This is true for bridges. So we need to recognize that there are a lot of challenges of implementing bridge monitoring in practice. But as I said before, so far the biggest barriers, let me see if I can. So far, the biggest barriers that the rate of benefit increase is just seems to be too slow. So we need to work more on that. That's the end. Thank you.